So welcome to this International Day of Women in Statistics and Data Science Conference. It's my pleasure to introduce this session. My name is Sofia Villar. I'm a program leader at the MRC Biostatistics Unit, which is sponsoring this session and a later session with postdoc work. So all of us presenting in this session and talking in this session are part of Efficient Study Design, which is a research group in our unit focusing on developing novel statistical methods to try and increase the efficiency of study designs across all stages of development and evaluation. And our program has 5 areas of interest, and we're hopefully going to showcase some of the things we're working on within the group through our brilliant PhD students. So without further ado, I'm going to start this session introducing our first speaker, Juliette Limousin. Juliette is a second-year PhD student. She's supervised by Dr. Li Su and Sean Seaman. Her research is primarily focused on causal inference for longitudinal studies, using target trial emulation to improve robustness and reliability to study results. Juliette's work aimed to bridge the gap between the theoretical statistical methodologies and the practical applications in public health and clinical research. With that introduction, I'll hand over to Juliette so she talks to us about her work as part of her PhD.
Thank you very much, Sophia. Let me just share my screen and make sure everything works before I start. Sophia, could you confirm whether you could see my slides in full screen?
I can see your slide in full screen, yes.
Amazing, perfect. Thank you very much. Thank you, Sophia, for that, and thank you to the whole organizing committee as well for this wonderful day. It's been such a wonderful series of panels, very interesting stuff. So without further ado, I'll be talking about today about
Juliette, there is a bit of a sound coming from your microphone. I'm not sure.
Okay. Let me try to suppress some background noise. Okay.
Thank you.
Great. I'll get back to my slides. Great. So this, inference procedures in target trial emulation with survival outcomes. This was work done with my supervisors, Li Su and Sean Seaman at the Biostatistics Unit. So to give you a bit of context, the main topics of interest in this work are causal inference, survival analysis, target trial emulation, and longitudinal data, just to put everyone in context. So target trial emulation has become a very popular approach for causal inference when looking at longitudinal observational data, and it has great applications to survival analysis as well. Now, in terms of estimation and inference using trial emulation approach, in this talk, we're interested in constructing confidence intervals of per protocol effect of sustained treatment compared to no treatment on survival outcome. So what would be the survival outcome had maybe contrary to fact someone had always been treated versus never been treated over a period of time? Now, the presence of time-varying confounding and dependent loss to follow-up in our longitudinal observational data mean that constructing confidence intervals becomes not so straightforward in this causal inference context. Now, before I go into the estimation and inference part, I'll quickly talk about sequential trial emulation, which is the approach that we took in this paper. So it's a special case of trial emulation where you can see in this graph, instead of having one single trial emulated from a time baseline 0 to suppose 3 time points, we're actually instead emulating a sequence of trials that have sequential enrollment times, so T0, T1, T2, which means that essentially we enroll patients to any trials that they're eligible to. So in this first example in the graph, you've got 200 patients eligible at a trial that starts at T equals 0, and 50 of them were actually never treated at that point. And if we decide that the eligibility for a trial is based on the fact that you were never treated prior to enrollment, then those 50 patients that were never treated could actually be enrolled into the second trial starting at t=1 as controls and remain as controls in that second trial, and so on and so forth. So basically, this approach has been shown to have a better efficiency than a single trial approach by basically increasing the number of patients that you see in treatment arms by doing this multiple enrollment scheme. Now, in our paper, the causal estimate of interest is the marginal risk difference averaged over a target population. So we define this marginal risk difference as the probability of the counterfactual survival outcome, whether you were always treated or never treated. Now, because we're interested in this per protocol effect of always treated or never treated, we need to censor patients when they are no longer complying with the treatment protocols for per protocol analysis. And so that kind of induces another sort of bias. And so to correctly estimate our marginal risk difference, we can use the approach of fitting marginal structural models that are weighted with inverse probability weighting. And so the inverse probability weighting makes sure to account for the time varying confounders that affect this treatment switching effect that might make someone come out of treatment protocol, and any sort of dependent sensory due to loss to follow that we might encounter as well. Now, the IPW-MSM approach is like the kind of probably the most popular approach in longitudinal setting in this sort of context. Now, in terms of building confidence intervals of the marginal risk difference, the two main popular approaches are first and foremost the robust sandwich variance estimator. It estimates the marginal structural models coefficients, variance covariance matrix, and you can use that to make some sort of parametric sampling of your marginal structural models variance, and then you can build confidence intervals based on that. The advantage of the robust sandwich variance estimator is that it accounts for the correlation that's induced from having your individuals be eligible and enrolled in the multiple trials that I'm sequentially emulating. Now, another very popular approach is non-parametric bootstrapping, where you bootstrap the marginal risk difference estimates and then you construct some sort of percentile-based confidence interval. Now, there are several considerations with these methods. So the first problem with the robust sandwich estimator specifically is that it doesn't actually account for the uncertainty in your IPW estimation. And so it's also quite a conservative estimate of my variance. And for non-parametric bootstrapping, although it does account for this uncertainty, it's an advantage over the sandwich estimator, it is computationally very heavy, whereas the sandwich variance estimator is a one-step estimator. So the non-parametric bootstrapping is computationally much heavier to construct confidence intervals from. And also, if you're dealing with small sample sizes, it might lead to ill-conditioned covariance matrices. And so you might not actually be able to construct a bootstrap-based confidence interval in some cases. There's actually no literature currently comparing these two methods in the sequential trial emulation context using IPW-MSM. And we also found that there was this method called the linearized estimating function bootstrap, which is used in survey data analysis. It's a computationally more efficient alternative to non-parametric bootstrapping, but it hasn't been applied in the trial emulation context. So not just sequential trial emulation, but target trial emulation as a whole. And we had also noticed previously in the sequential trial emulation paper that jackknife sampling was also considered, so we did include that in our analysis as well. So the aim of our paper was to compare these statistical methods for constructing confidence intervals of the marginal risk difference using the sequential emulation trial approach for causal inference on survival outcomes. And to do that, we conducted a thorough simulation study. So just to introduce some quick notation, in our simulation, we simulated some data sets with 5 time points. And so we were able to therefore emulate 5 sequential emulated trials. We have outcome indicator, survival outcome indicator YK, where YK equals 1 if the event occurred within the time k plus 1. We're dealing with a binary treatment AK. And we have a time-dependent confounder X1K that is dependent on treatment history. and we have a time invariant or baseline confounder in our data sets. Now, before I go into this, for those of you who are familiar with directed acyclic graphs, this is an example of such DAG with our data setup. I've just restricted it to 2 time points here, but we can clearly see the treatment confounder feedback where the current confounder is affected by past treatment, and past treatment is itself affected by a confounder. Now, in our simulation study, we assessed various types of data scenarios. By that, I mean that we change different aspects of the data sets to account for how those affect our confidence interval performances. So, for example, outcome prevalence, how many people had the outcome in the data set. That could be ranging from low, medium to high. Patient sample size, confounding strength, which is the strength of this confounder X1K on the prediction of the treatment and the outcome. Treatment prevalence, so how many people initiate my treatment, so low, medium, and high. And so with a median treatment prevalence, we'd expect the data set to be having quite balanced treatment arm numbers. Now, in each data iteration for the Monte Carlo simulations, we estimated the marginal risk difference, and we concentrated on our target population being patients eligible in trial 0. That's because it's the trial 0. By that, I mean the trial that has enrollment at the baseline of my data set. And that's because it was simply just a data set that had the longest time horizon. So it was easiest to estimate and construct confidence intervals from. And we did that using the IPW-MSM approach we mentioned earlier. And then we constructed 5 types of confidence intervals of the marginal risk difference for those patients. So first, using the robust sandwich variance estimator, then non-parametric bootstrapping, the linearized estimating function bootstrapping, and we did this on the marginal structural models parameters, because the linearized estimating function bootstrapping is based on the linearization of my coefficient estimation. And that could be done either on just the MSM parameters or on IPW and MSM parameters. So supposedly with this green approach here, it will be computationally even more efficient than the purple approach here, because we don't have to re-estimate the IPW models, because we're doing a linearized approximation of the parameters. And then we also included jackknife sampling only for small sample sizes, but I will show you the results in a second, but the jackknife sampling results won't be included in my plots, but I'll make a note of them later. So, apologies if the plots are looking a bit blurry. I hope it's fine for everyone. I didn't realize that there was an issue with quality. But so I'm focusing here on some scenarios. So basically, in the top left, we have a top line is small sample size, so 200 patients. Bottom line is 5,000 patients. Here on the left half here, we have low confounding. And then right half, we have high confounding. Now, I'll quickly make a note of this, that confounding strength didn't seem to affect our results much, so we can actually concentrate on one half of our panel. And then each column here represents low treatment prevalence, medium treatment prevalence, and then high treatment prevalence. Now, I understand that this is a lot to take in, so I have a summary of the results and key takeaways after this, but I just want you to concentrate specifically on this purple line that overlaps the green line. So our first finding was that doing the linearized estimating function either just on the marginal structure model or also with the IPW didn't really make a difference. And so I'll just be mentioning that as LEF confidence intervals. But I want you to note the coverage over the follow-up time of these confidence intervals that are definitely performing better for LEF in these small sample size and low to medium treatment prevalence scenarios. And with high treatment prevalence, we were finding that actually there was a lot of data sparsity, because treatment prevalence tended to actually because the treatment had a positive effect on reducing risk, we were just not having having too much data sparsity issues to be correctly estimating the marginal risk difference. So that affected the confidence interval construction as well. But focusing on the low and medium treatment prevalence results, as you can see, the linearized estimating function shows a pretty good coverage results compared to the non-parametric bootstrap and the sandwich variance confidence intervals in small sample sizes. And then when you increase the sample size to 5,000 for here, for example, all the methods kind of perform similarly, and that is to be expected because these are all based on asymptotic results. If this was all shown on low event rates, so about 2 to 5% of outcome prevalence, and then if you increase the event rate, we expect the estimation and inference to become better because of we're seeing more events in the data sets. And still in this case, we're still seeing better performance for linear estimating function confidence intervals in the small sample cases and low to medium treatment prevalence, sorry. So to summarize all this, linear estimating function bootstrap provided better coverage than sandwich confidence intervals, which were kind of accepted as the default method currently in the literature, specifically in small and medium sample sizes, low and medium outcome event rates, and low and medium treatment prevalence. Now, non-parametric bootstrap, which is also very commonly used, were considerably affected by treatment arm imbalance, and so the treatment prevalence and data sparsity, particularly in scenarios with low event rates and small moderate sample sizes, whereas LEF bootstrap was performing much better in such scenarios. Now, I quickly mentioned jackknife confidence intervals. We did see that they achieved nominal coverage and for small sample sizes and low treatment prevalence, but they were quite sensitive to treatment arm imbalance. And depending on kind of which approach you took with jackknife, it could also lead to some construction failures with just not being able to construct the confidence interval properly. And so that we didn't really see much advantage of that approach, essentially. Now, all methods perform poorly when treatment prevalence were high and sample sizes were small due to the data sparsity issues. And as I said, jackknife and sandwich confidence intervals faced numerous construction failures, making them quite impractical for use. Now, for large sample sizes and as you increase the event rate, the outcome prevalence, the sandwich confidence interval would still probably be the method to be advised to use because it has the advantage of being much more computationally efficient than any of the methods. So because we were seeing that at large sample sizes, the results for the coverage were quite similar, one could still go for the sandwich approach in large sample sizes. Now, the key takeaways are for this paper that I want our audience to take is that LEF bootstrap can offer a useful alternative to the more accepted methods of sandwich variance estimator and the non-parametric bootstrap, especially in small and medium sample sizes, and that one should really carefully consider the different aspects of your data sets, so sample size, outcome event rate, and treatment prevalence when selecting a confidence interval construction method in sequential trial emulation. Now, to finish off, I want to note that all this simulation work was enabled to be done much more smoothly thanks to the trial emulation R package that's been developed by my supervisor and her collaborators, Isaac, Sean, Runak, and this package is now available on CRAN, and it's still being developed. And if you're interested in more development side, it's available on GitHub. And so the utility of this trial emulation package is that essentially the sequential trial emulation approach requires some sort of a lot of data manipulation to get to the point where you can have these sequentially emulated trials. So it does the expansion for you and then the estimation and inference as well. And so it automates the analysis of sequentially emulated trials. Now, many thanks to my supervisors, Lee and Sean, and the collaborators for the package, Isaac and Runak. And here is a link to the preprint if you're interested, and the paper has been submitted to a peer-reviewed journal as well. Thank you very much, and I'm happy to take any questions.
Thank you very much, Juliet. That was a very nice presentation and spot on with time. We have time for questions. If anyone wants, you can type in. If we don't get to answer them now, we can go back at the end of the session. While I let the next speaker get ready, can I ask you one question, Juliet?
Yeah, of course.
So you talked about the computational efficiency of the sandwich estimation versus the bootstrap. You also said that sequential emulation is appealing because it can offer efficiency gains, but I imagine the efficiency gains are in being able to estimate more precisely. And
yes, it's not computational efficiency, it's estimation efficiency. Yeah.
Did you look at that by, for example, comparing in a setting sequential emulation versus a one-off emulation, and to try to quantify this efficiency gain?
I haven't quantified it, but it's definitely the inefficiency, so to speak, is definitely coming from this data expansion and data manipulation that you have to do in order to set it up in a way that is that works with the sequential trial emulation, because you have to include a column for eligibility for each of your sequentially emulated trials. Now, I know that there has been work to make sure that this expansion can be done computationally efficiently in the package. So I believe there is like a parallelization of the task that can be done. So by essentially kind of cutting the data set that you're providing the package into chunks, the package is then able to parallelize the work of preparing the data set for sequential trial emulation. But I think that will be actually a pretty interesting measure to probably include as well. Yeah.
Food for thought. Thank you again for your talk, and please type in questions for Juliet if you have any. She'll be around until the end of the session. So we go on to our next speaker, Bethany. Bethany is a third-year PhD student at the MRC Biostatistics Unit. She's advised by Dr. David Robertson and myself. Her research focuses on testing policies for epidemics, particularly focusing on pool testing policies. Her work involves developing agent-based models for evaluating different testing methods. Bethany has received one of the 6 travel grants from the IBS British and Irish region for career young biostatistician. She will attend the International Biometric Conference, so if you go, please go to hear her presentation. The conference will take place in Atlanta in December. She will now be giving a talk on her work on evaluating testing policies for epidemic management, focusing on the use of pool testing as one of the elements of these policies. So Beth, the floor is yours.
Okay, show the screen. Hopefully that is now visible. I muted it, but still. Should we mute yours?
Sophia, you need to mute your sound as well as your microphone.
Okay.
I'm Bethany, and I'll be presenting work for my PhD on evaluating pool testing designs in the community and healthcare settings, and presenting work from 2 papers. So first of all, I'll talk about the motivation behind the project, why it's something we're interested in, before going into introducing what actually pool testing is, and then talking about the model that we developed in order to analyze pool testing in these different settings, and then talk about what key factors we were thinking about when we were looking at these different settings and different time periods. So obviously testing was very critical during the pandemic. This is not only for prevalence calculations and nowcasting and forecasting, but also as part of managing the pandemic. And this is particularly the area that we're interested in looking at. So the issue was this is during the pandemic, reagents for PCR testing, which is the testing we had right at the start, and the most accurate form of testing came into short supply. This meant we had tests piling up that couldn't be completed, and then we had to halt testing. Therefore, pool testing, which is a way of testing loads of individuals with a single test, was suggested as a way of saving on these resources. So as I will explain in a bit more detail later, pool testing is optimal in a setting of low and constant prevalence, which is obviously not the case always with COVID-19. So a large part of our work was looking into when we don't have this case, can pool testing still be beneficial to be used? So as I just said, pool testing is where multiple individuals are tested our samples are combined and tested with a single test. So in this case, we have 9 individual samples being combined and tested together. So there's lots of ways of testing, of completing this pool testing, but we're going to look at the Dorfman scheme. So that's the first pool testing procedure that was said, and it's the one most familiar to laboratories. So in this scheme, if the pool comes back as negative, then all individuals in that pool are marked as negative, and then they don't have to go through any more testing. So therefore, we've tested 9 individuals with just 1 test. And then if the test is positive, then all individuals in the sample are tested individually. So even though these individuals got a positive pool test, they'll only be marked as positive if their individual is also positive. And then this takes 10 tests. So we can easily see how we want to have a low prevalence in order to be only using this 1 test for 9 versus 10 tests for only 9 individuals. The reason why we want a constant prevalence is because when we're deciding on this size of this pool, it's helpful to have this constant so that we can have this optimal pool size and it's not changing quite a lot. So this is the stages that we used to build both our models. So we used agent-based modeling in this. So these are, you don't have to go through in order, but this is just how it will go through in the slides to make it a bit more sense. So by relationship network, we talk about who are the individuals in the model and how they connected to the others in the model. And then this is important to include because we want to understand how the disease spreads throughout the population. And then we have dynamics. So that's of the individuals who are infected. How do they go through that? How do they move through that infection? And then we're also going to talk about this about what factors we considered when looking at each of these settings. So, for example, we might look at the types of testing available. So PCR versus LFD, or compliance, so whether individuals comply with our testing stuff. So we'll talk a bit more about that stuff later. So this is the relationship network for the community setting. So in the community, we simulated 500 households. So that's about 1,100 individuals. And then the age and household size was taken from the UK 2011 census. So that means if in the census, about 20% of households were 1 parent, 1 child, then about 20% of households in our simulated set would be 1 adult, 1 child. And then you might be able to see these grey lines between individuals in the diagram. So these are the connections between individuals. And then these are separated into 2 categories. The first of this is transient connections. So that's just bumping into each other at a supermarket or getting on the same train. And then we also have known connections. So the most obvious of this is, for example, a household where they're all connected to each other in the household. But we also have workplace, so adults and some of the elderly population are connected to individuals in their workplace, not the whole workplace, but an average of 15 individuals, as that's expected how many would share facilities with each other. We then have for the children in the model that they go to school and are therefore connected to an average of 30 individuals to show the individuals in their class. And then additionally, we have friendship connections between individuals in the model. So then we have the healthcare setting, which is obviously a little bit different because we have separated into these 2 types of individuals, healthcare workers and patients. So we simulate 1,000 beds, which the patients can go into, and 8,000 healthcare workers. And of these beds, they get separated into wards, and within those wards, they're put into bays of 6 beds. So obviously, because we have these 2 different types of people, they have different connections in them. So the healthcare workers can get infected by, of course, other healthcare workers, and then the patients they treat, as well as the visitors visiting the patients. But what makes them different is the fact that they have 12 hours on shift where they can get infected in the hospital, and 12 hours off where their probability of being infected is determined by the outside prevalence. And that's different to the patients who will remain in the hospital until they're discharged. And then they can be infected by individuals in the same bay as them, in the same ward, as well as the healthcare workers and the visitors coming in, where also the probability that a visitor is infected with COVID is also determined by the outside prevalence. So another distinction in the healthcare worker population is that 35% of the healthcare workers are ward-based, and then the rest of them go throughout the whole of the hospital. And you can kind of see that, for example, a consultant might remain on a single ward, whereas a cleaner, for example, would go throughout the whole hospital. So we'll talk about that a bit more later. So next, it's the dynamics. So in both papers, we follow this trajectory where most individuals start off as acceptable, apart from any initial infected. They then get exposed, so they've had contact with an infected person. And then after an incubation time, they themselves become infected and can then go on to infect others. And then this can either be with symptoms or without. So it's two different trajectories coming from exposed. And then after their infectious period time, they then go to recovered. So you can add an extra line from going to recovered to acceptable, but we only have this going for about 100 days. So that's not quite enough time for individuals to recover. So this is done two different ways in each of the papers. So in the first paper, in the community setting, we simulate for each individual, we draw from a distribution that, for example, their incubation time. And once that time's passed, they move between states. And then for the later hospital paper, we model each individual's CT value, which is kind of, which is related to the testing. And it's kind of a measure for their viral load. So you can see where each individual is in this process, but also it means that you have how infectious they are changing over time, which is information we had later in the pandemic. So unfortunately, I don't have time to go through the full results for both of the papers, but I thought I'd have some results here to show what sort of things we were looking at. So in the community setting, so this is looking at the expected total infections against the proportions of symptomatics. And we were looking at the comparing the symptomatic testing with the pooled random testing. So that's randomly pooling individuals from the population and testing them together. Individual random, so that's randomly choosing who to test from the population. And we looked at this for 5 tests per day and 20 tests per day. So that was translating the testing capacity that the UK had to our population of around 1,100. So this is what they varied between. And we wanted to understand when should this pool testing design be used and when should the symptomatic, which was actually used, be thought of instead. And we surprisingly found that actually symptomatic testing performed pretty well. So for over 30% of cases being symptomatic testing reduced infections more. And we can kind of understand that by thinking that when we have individuals who are symptomatic, who are going to, we kind of have information about that they're very likely to test positive. So we're not kind of wasting tests. And then we kind of looked at the case where we had compliance, where individuals who didn't have symptoms went to go get tested. And only for relatively low amounts of non-compliance in that did pool testing start to do better. And then you can kind of see that that information we had from individuals being symptomatic, we'd reduced it down, and then pool testing was a preferred strategy. So then when we started looking at the hospital setting, so just to explain this chart, so the further the lines are to the outside, the better they are. So if you have a triangle that completely surrounds the other triangle, it performs better in all the metrics we're looking at. And the reason why I've included this is because a massive thing when we're deciding on policies is, well, what is our metric of interest? And then we can see in this diagram that the preferred strategy, if we look at infections and trying to reduce down infections, is different to what we'd prefer if we're looking at cost. And just to go through what each of the testing policies we're looking at here, is we were looking at pool testing as an addition to a symptomatic testing policy, because obviously we'd seen how well a symptomatic testing policy actually does. So PCR and PCR only, sorry, and PCR and LFD. So the difference between that is in PCR, you have your PCR pool test, and then when you test individuals by themselves, you use a PCR. Whereas in the PCR and LFD, when you do that individual testing, you use LFDs. So we really wanted to understand the difference between the PCR, which is more accurate, against the LFD, which is quicker. And the second part, which is this full, means which healthcare worker, sorry, in this hospital are you testing? So full means all of them. So that's those who are in the wards, but also go throughout the whole hospital, or just ward-based. And we see in most cases, this ward tends to do better. And then again, it's because you've got more information. Those who are in the same ward are more likely to test positive or be positive, sorry, at the same point. So grouping them together made improvements. So we also looked at this for combining it with non-pharmaceutical interventions, and then looked into different levels of prevalence outside as well. So what we're hoping to do next is, so our first paper was looking right at the start, where you have an emerging epidemic, you don't have much testing capacity, and also not much knowledge. And then in the hospital paper, we looked both at the this initial period, but then looked also at the later Omicron, when you had more knowledge and more testing resources. And what we're really interested in looking at next is when we're into this section, into this section here, where, for example, this is using the ONS estimates. So your ONS estimates have gone, so you have less information to use, although you still have all this information about the dynamics. And how can we perhaps think of a testing policy here using pool testing, particularly if we're thinking about at-risk populations. And we can also think about this not only for post-pandemics, but also in stuff like flu. So that is an area that we're interested in looking at next. So in conclusion, so pool testing is a method of testing multiple individuals with a single test, and it does have the potential to test more of the population, which is really important when we're in this case of a low testing capacity. However, there's a great number of reasons why you would or would not use it. Some of them are written on the screen, but as going back to that last diagram I was talking about with the hospital setting, is these metrics of interest. So for example, if you have a really limited budget, you might not be able to have a pool testing scheme on top of your symptomatic testing. So thank you very much for listening, and then feel free to add any questions to the chat.
Thank you, Beth. That was a very, very spot on in time as well. Please type in any questions. I'll make a short one. Could you comment a little bit on how you decided the pool sizes in the simulations and what effect would have, would you be worried about effects like contamination if the pool is too large and so on? Could you just say something around your thoughts on that?
Yeah, so we used a pool size of 12, which was coming from the NHS and what they used and recommended in their work. So obviously you have the issue that as you go for a larger pool size, you can have dilution effects. So there's too many negative pools, too many negative samples in the pool. So then you can't identify the one positive sample in it. So even if you have a very low prevalence and it may seem beneficial to go for a larger pool size, the reason why we capped it at 12 is to prevent issues of this dilution.
Thank you. That's very useful, and thank you for the talk again. We'll go now to our final speaker of the session, Zijing Chen, and she's also a PhD student within our group. Her research focuses on dose-finding study in early phase clinical trials design. She's supervised by Dr. Pavel Mosmanov and Professor Thomas Yaki. She previously worked on addressing missing data problems in response adaptive designs. She's very passionate about the challenges that adaptive designs in clinical trials bring, and she hopes to contribute to advancing to develop innovative approaches that enhance patient outcomes and accelerate drug development processes. So welcome, Jijing, and thank you for doing this. So the floor is yours.
Yeah, thanks, Sophia. Can you hear me from online? Yeah. Okay. So hello everyone, I'm Xijing, and I'm currently a PhD student from MRC Biostatistics Unit, and I'm supervised by Pavel Montgonov and Thomas Yaki, and my project is about today I'd like to have a talk about using ctDNA as a novel biomarker of efficacy for dose-finding designs in oncology. So here is the background. The development of oncology drugs is challenging with high attrition rates and low rates of approval. And alongside the pipeline of drug development, clinical trial designs are of critical importance. And early phases of clinical trial designs are normally focused on finding an optimal dose, which can be safe and active simultaneously. That is, dose-finding trials in oncology always aim for a safety and efficacy trade-off of an optimal dose. In recent years, clinical trial designs of biomarker research in oncology has been very popular. Mutations in cell-free DNA are highly specific markers for cancer, and this has gave rise to the term circulating tumor DNA, that is ctDNA, and it has been regarded as an effective prognostic and predictive marker for cancer detection. So the development of modern technology like liquid biopsy allows the early detection of early readout of ctDNA, which can be used as kind of indicator of treatment response. So the objective of my project is to evaluate the information introduced by biomarkers such as ctDNA and its use in those finding studies to see how much it can improve those finding trials. Here is an illustration of our motivation. So in those finding studies, here in this example, we have 3 cohorts of patients and 3 patients in each cohort. We have this, each cohort of patients is recruited every treatment cycle, that is 4 weeks. And we have access to toxicity outcomes, A, 4 weeks after recruitment, while we don't have the access to efficacy outcome, B, until 12 weeks after recruitment. So we see there is a problem, that is late onset problem, that the duration of treatment will be fixed at 12 weeks after recruitment for each cohort. And suppose we are at week 8 here. When we start to recruit cohort 3 patients, we are not able to use the information from cohort 1 just because we are still in the waiting time between week 4 and week 12. We still need to wait until week 12 to make full use of the information about cohort 1 patients. So that is kind of a waste of time. That is so-called late onset problem in those finding studies. So traditionally, we can use a Bayesian adaptive dose finding design, the FTOC approach, which helps us to model the correlated binary efficacy and toxicity outcomes. There are 2 paths. One is that we firstly model the relationship between doses, DJ, and the probability of events, toxicity and efficacy. Secondly, we will have a joint probability function, which helps to capture the relationship between those events. Events A or B for the event of toxicity and efficacy. In the end, we will be able to find the optimal dose, which is the dose that maximizes the utility, which is defined based on the joint probability function. Yeah, that is the FTOC approach, which was proposed in 2004. So after we introduce the biomarker information, we are able to have a biomarker-informed FTOC, BMI FTOC approach. Here, early readout of ctDNA can be used to predict subsequent responses to treatment. And ctDNA of patient I at time t can be introduced as a proxy for not yet available efficacy outcomes if it is large enough. So we see here is a replacement that we are trying to apply. If the ctDNA is large enough, larger than a pre-specified threshold epsilon, we will count there is no efficacy. Not yet available efficacy outcomes. In the end, the regularly available ctDNA values, CTJ, will be able to reflect the lack of response profile of the specific dose J in this manner. So now in our previous example, if we have this early indicator of lack of response based on the information provided by ctDNA, we see that at week 7 for cohort 1 patients, at week 7 we already have this lack of response information based on ctDNA, and cohort 1 patients will be able to resort to other alternatives instead of still keeps waiting until week 12. And at week 8, when we try to recruit cohort 3 patients, we can make use of the information from cohort 1 patient. So their dose administration will be based on more information, so we can expect better dose strategy for cohort 3 patients. Of course, and the duration of treatment for cohort 1 and 3 will be reduced to 7 and 8 weeks, that is here and here, respectively, instead of the fixed 12 weeks. So we can see this introduction of ctDNA, even though in a conservative way, the one-way information, it can only indicate lack of response. This kind of introduction could help the current patient to have an early decision about whether to continue or come to other alternatives, and also helpful for the upcoming patients to have a better dosing strategy, and also helpful for the investigators to expect a faster dose finding trials. That is the main idea of our approach. So in order to evaluate the performance after introducing ctDNA, we have conducted a comprehensive simulation study where we have different kinds of considerations. First, we need to specify the prior distribution for different parameters. And second, we need to specify the corresponding parameters in the trial design, including cohort size, trial size, and also epsilon, that is a threshold for the indication from ctDNA, and also the threshold of minimum efficacy or maximum toxicity, so on and so forth. What I want to highlight is a setting specification for the trajectory of regular ctDNA. Since we are still in the stage of simulation study, we don't have the real data, so we try to specify different settings of the trajectory to capture the reality as much as possible. And also we have different set specifications for scenarios about the dose profiles, including both efficacy and toxicity. So for the simulation settings, we have this polynomial regression to simulate the trajectory of the mean values of ctDNA with time. So here are 4 different kind of settings for the trajectory. The black line reflects the possibility of treatment resistance that the ctDNA keeps increasing. That is, if the treatment didn't work for the patients. The second one, the red line, is a type of response to treatment. So the ctDNA keeps decreasing, which is the ideal result that we want to see in patients. And also there is a combination of both. So the green curve, resistance after response, and the blue curve, response after resistance. So we try to use these trajectories to do data generation. And then we also have different kinds of simulation scenarios. So we have 5 scenarios corresponding to the dose profiles in terms of toxicity. Take an example, T2 indicates the scenario where 2 doses are safe. And similarly, on the right-hand side, there are 5 scenarios corresponding to the efficacy profile of our 4 investigated doses. And take E3 as an example, it indicates a scenario where 3 doses are active or efficacious among the 4 investigated doses. So we see these scenarios are specified by the number of safe doses and number of active doses based on the threshold value that I specified in the title. And we can tell that we are under the assumption of monotonicity in both toxicity and efficacy. So now we can move on to the simulation result. The first metric we evaluated is the proportion of correct selection. So considering both efficacy and toxicity, we have 25 scenarios, that is 5 times 5 in total to be evaluated. Here we have 2 types of scenarios. For the scenarios with gray background, that are the scenarios where there are no optimal dose because there is no overlap between safe doses and efficacious doses. And for the scenarios with white background, we have the optimal dose denoted in bold in the brackets. Yeah. And in terms of the metric proportion of correct decision, for the case with gray background, we would like to have early stopping because there is no optimal dose. While for the other scenarios, we just want an improvement of optimal dose. Yeah. So this the way to look at this table is that this reflects the average difference of the biomarker informed F-talk approach from the F-talk approach in the proportion of correct decision. Let's take several examples. If we look at here, T2E1, it is a scenario where dose 1 and 2 are safe doses, while dose 4 is the efficacious dose. So in the end, we would like to see early stopping. In the end, when we compare these 2 methods, we see the proportion of early stopping is improved by 9.8%, while the BMI F-talk approach. Another example here, T4E3, BMI F-talk is more likely to recommend the optimal dose, that is dose 4, by 9.3%. So overall, for all of these 25 scenarios, the majority will have an improvement of the proportion of correct decision, that is, which indicates that the information from CTDN helps a lot to do the correct decision. And also, of course, there are some kind of negative values, which could be just because the optimal dose and a competing dose are very similar to each other. They are so competing. In the end, the introduction introduction of CTDN values can bring not only information but also a bit noise. But I mean, this kind of decrease of the proportion of correct decision are not so large, so it is not so horrible. And the second metric we care about is the duration of treatment. So here is a figure for the average difference of the BMI F-talk from the F-talk in the duration of treatment. And we have tried to distinguish between the active doses and inactive doses. It is very clear that for all of the scenarios, the duration of inactive doses will be reduced quite a lot, more than 3 weeks, let's say. And also the duration of active dose might be reduced a bit as well. I mean, in the end, BMI F-talk approach would end up with a shorter trial. Yeah. So we can see the improvement in terms of the duration of treatment in this figure. Last but not least, we care about the proportion of toxicity because we don't want to bring too much harm by the BMI F-talk approach. In this figure, we see that the proportion of toxicity has not been increased too much. I mean, they are kind of under control in terms of the final result. Finally, we see that with shorter to evaluate information, biomarker-informed dose-finding designs can bring about a more efficient and rapid dose escalation procedure. For the next enrolled patient, they can be assigned to better doses based on more information from early readouts of ctDNA, and investigators can expect a faster trial. In the end, the current patients can benefit from early termination or early stopping of the treatment and turn to some alternatives instead. So yeah, we see the introduction of a biomarker can help to improve early phase dose-finding clinical trial designs. That's all. Thank you.
Thank you, Ziqing, for your talk. And we only have 3 minutes, so I'll make a quick question and then we'll wrap up. You talked about utility functions for efficacy and toxicity. What kind of utility function is this defined for every patient the same, or when you're doing the dosing?
Yes, it is kind of a function that is a control which is based on both toxicity and efficacy. So it could help to reflect both profiles of a specific dose.
Thank you. Thank you so much. So I want to finish thanking Juliette, Bethany, and Ziqing for a lovely session. And please contact them if you have any questions around their talks. And again, enjoy the conference and looking forward to the next session and the next chair. Thank you.